My name is Herminso Villarraga Gomez, and I am with ZEISS Industrial Quality Solutions. The topic of this presentation is extending the measurement capabilities of high-resolution X-ray computer tomography microscopes to dimensional metrology. And I like to start this presentation with a little bit of history of X-rays. So let me go back in time to November the 8th of 1895, when this guy, Wilhelm Röntgen, discovered something he called X-rays. That was a little bit over 125 years ago, and since that date, it had changed the way we used to see the human body. X-rays became an important diagnostic tool in medicine, allowing doctors to see the interior of a human body without slicing or cutting it wide open with surgery incisions. And in 1971, the first X-ray computer tomography system for creating a full 3D image visualization of the interior of a body was created. That was a machine designed by Gottfried Hounsfield in the UK. Years later, Hounsfield will receive the Nobel Prize for his invention, along with Alan Cormack. Again, medical applications came right after that, but also the non-destructive evaluation community started using this technology to see the interior of manufactured parts and to inspect them for all kinds of possible defects like void analysis, crack detection, thin wall assessments or thickness analysis, and also to check the interior of electronic components. And since around 2000, people have been using this technology for industrial metrology. There has been a growth of X-ray CT applications for dimensional measurements. In the traditional micro-CT world, the main approach is to use a projection-based system that is basically composed of an X-ray source and a detector and a rotational stage to place the part. But the imaging capability, resolution capabilities of such systems can be limited to something in the order of 2 microns, in the best case scenario. But there is one possibility to improve things and deliver sub-micron resolution capabilities if we use 3D X-ray microscopes. The main difference of the so-called 3D X-ray microscopes as compared to the traditional projection-based systems is that they include a set of lenses that are optical magnification capabilities additional to the geometrical magnification to achieve sub-micron resolutions. This example shows a typical workflow, how you can scan a full device, such as a smartphone, without destroying it, and using the zoom lenses of the 3D X-ray microscope, scan small regions of interest, such as the inside of BGAs. And you can check for all kinds of defects, such as porosity, or change the zoom in to check even smaller features, like the connections of the vias that connect different layers in the device. Using the same principle, you can explore different region of the device, such as the camera lens module, for assembly inspection of the lenses, and of course, to use this information for the enhancement of the camera designs in the cell phone image quality. Now, you have probably seen that we can get great images, but can we measure at high resolution with 3D X-ray microscopes? And this question alludes to the metrology terminology. Yes, we can measure. In fact, you can see a scale that we can put as to associate the dimensions of the imaging, but how accurate is such a scale? When I'm asking this, I'm basically asking, can we do high precision metrology with 3D X-ray microscopes? And again, the answer to this question is yes, because we found a way to do it with a metrology solution that can be implemented in 3D X-ray microscopes. We created a workflow called the Metrology Extension that to add measurement accuracy specifications to the ZEISS Xradia Versa microscopes through a statement of maximum permissible error using a tiny multisphere phantom. To develop the verification phantom of the Xradia Versa, we use the large experience we have in metrology. And you can see different phantoms that we have used in the past for other types of X-ray systems, such as the Metrotom. But all the way to the right, you see a very small phantom. It's called the XRM check. It's composed of 22 ruby spheres of 300 diameter each contains a cylindrical volume of about 4 millimeters diameter. And we are interested in measuring the center-to-center distances to create something, a verification chart like the one that you see below that is called a trumpet plot, which is that we see here. And as you can see from the top picture, the XRM check phantom fits in the top of a finger. So you can get an idea of how small this is. And with this, we are able to measure different distinct number of lengths in the sphere phantom to measure at least different distances in a total of 7 different spatial directions to follow the VDI-BDE 2630 guidelines, which are guidelines for X-ray dimensional measurements that are out there. The ASME has designed a new guideline that was released recently, at the end of last year. Anyway, following those guidelines, we can provide a sphere maximum permissible error or MPE specification of 1.9 micrometers plus L over 100. And this L is the dimension that you are intending to, that you are trying to measure. And this is the only solution of its kind for 3D X-ray microscopy, meaning that you have a combination of microscopy and metrology. In this video, the metrology workflow is presented. The first step creates a distortion map of the detector using a grid array to correct geometrical distortions in the X-ray image. Then, a multi-sphere phantom can be placed in between the source and the detector to start collecting radiographic projections, which are being used for the tomographic reconstruction. The 3D data is opened with a metrology software, also developed by ZEISS, to make comparisons against the nominal geometry and compare to calibrated data that is performed in a National Institute of Metrology, in this case in Switzerland. And the software is going to compare the center-to-center distance with that CMM or reference tactile data that has a very low uncertainty in the order of 140 nanometers. So this comparison is very good to create a graphical report to determine the accuracy verification of the dimensional measurements with the 3D X-ray microscopes. Once the system is verified, then if it passes the verification stage, dimensional measurements can be made in other parts with enough confidence. And this is one typical example, which is the smartphone camera lens assembly, which, as you can see, has a geometry that is not accessible to traditional tactile or optical CMMs. In the assembled state of this lens model, a non-contact and a non-destructive measurement method is required. There is no way to access the internal features of the lens with a tactile probe, nor with an optical or vision system, without disassembling the sample. So 3D X-ray measurement is the only way to inspect this sample for dimensional metrology without destroying the assembly. And there are other types of examples in which the metrology extension for 3D X-ray microscopes can be used. For example, a small plastic injection molded part or a fuel injector nozzle, which, as you can see, have all of those have internal features that could not be easily inspected unless you use a non-destructive method as X-rays. And to have accurate measurements, now you have the metrology extension for 3D X-ray measurements. Here is a summary of the unique capabilities. We preserve the well-known high-resolution imaging capabilities of the 3D X-ray microscopes. And this allows us to reveal the smallest features of the part at high resolution. And in addition to that, now we can measure them accurately. Now we can do high precision metrology tasks with the 3D X-ray microscopes, highly repeatable and highly accurate, using a simple semi-automated workflow. And we have now the highest accuracy specification of 3D X-ray metrology, with the unique capability of merging microscopy and metrology. So this is basically a summary of how to add high precision metrology to high resolution X-ray microscopy. And if you have any questions, I'll be happy to answer.